Alright everyone, so this is the second page of your quiz. Now this is just a little bit different, but actually we'll see as we get to C and D that we know a lot about this type of problem because of what we've done before at the beginning of the year. So first, we're asked to describe the motion of the object modeled in the graph. So the object, all they mean by that is the line. So assume that it's some type of car, it could be quite literally anything that you want, it's just some object that they have represented by the line. So just imagine some kind of object moving along this path. And this path is going to tell us how far it went, that's our position, in a certain amount of time. Okay, so first things first, where are we starting? Well, we see here that our y-intercept, or where it starts on the y-axis, is at 15 meters, right between 10 and 20 meters on the side. So we would write, starting at 10 meters, wide, 15 meters. Then we want to figure out, well, is the object going in a positive or negative direction? And since we're going up and to the right, we know that's positive. It's going down the time, but up in a positive direction. The object travels in the positive direction. And then we want to tell a story about where it ended. So if we told us where it started, we told the direction that it was going, but we didn't say where it ended, then we wouldn't have the complete graph. So then where did we end? We will see at the top of the graph end at the very top, and that's at 50 meters. So it says arriving at 50 meters after, and we want to make sure that we're representing how long it took, otherwise we wouldn't know where exactly to put our line. So we can see that after 1 second, 2 seconds, 3 seconds, and actually it stops. When it hits that 50, we go down. It looks like about 3.5. So after 3.5 seconds. Okay, so that's all you have to do when you're reading this graph. You're just interpreting it and giving me in words what is happening. Now, this one gets a little bit more challenging when we talk about the average velocity. Really, the slope, as we talked about in class before, the slope of the graph of the rise over run actually gives us average velocity. And a lot of you might think, oh, why, or how is that possible, or how can I remember that? Well, always remember, when you're looking at a graph, whether it's position versus time, or velocity versus time, this is going to tell us a story. So if we have a straight line, and we can look at it being position over time, well, all we've said before ever is if you're running on a track, running down a field, or if you're going in a car, you're covering a certain amount of distance over a certain amount of time. And that's all that this slope tells us. It's our rise, which is our position, over our run, which is our time. And that, therefore, is what the velocity that we've constantly been saying is the equation of a change in x over t. Change in position over time. So, velocity equals slope equals change in x, or position, over change in t. Remember that delta sign just means change in. Okay? So now we want to look at where we started, or where we finished. It's our y2 minus our y1. That's our 15. Because we want to go backwards somewhat, so we want to take our final point to our initial, and we're going to work backwards from there. And then we have to look at our time, so that we finished at 3.5 seconds, and at 0 seconds we were at 15. So do you see how you have your 50 meters and the 3.5? Those go together. At 15 meters, that's where we started, and that was at 0 seconds because we hadn't gone anywhere yet. So if we do the calculation on that, that would be 35 meters. Remember, it's in meters, don't forget your units. Over 3.5 seconds. And if you do the math and figure that one out, you'll see that you have 10 meters per second. And that is the object's velocity. Now for C and D, we have the mathematical expression, and we've seen this quite a few times over. And this actually gets to where we were talking about in last class and taking notes, that our final position, right, that's our 50 meters, so we know we have to talk about that, equals our slope times time plus the y-intercept, where did we start? And although that would be correct, that would be the correct expression to describe this type of graph, we have to personalize this equation, otherwise it wouldn't be describing this specific line that we have here. So all we have to do is plug in what we know, and that would be our slope, which we just figured out, would be 10 meters per second times time plus the y-intercept we know to be 15 meters, because that's where we started. So with this equation, you could figure out a couple of different things, but this would be your mathematical equation. And to give an example of that, that's where part D would come in. So taking this exact equation, all we have to do is plug in t equals 10 seconds, because we are only asked to determine where that object's position will be at 10 seconds. And because we just created that expression, an expression in math can be used universally when you have some key components like the slope and the y-intercept. If we know the rise and the run, and we know where we're starting, well, we can just plug in after a certain amount of time where an object will be. So let's do that. So x, or the final position, equals 10 meters per second. And then it's asking us at 10 seconds, so all we do is plug in 10 seconds plus the y-intercept, 15. As you can see, I'm literally just plugging in straight across. Do that calculation, that will turn out to be 115 meters. And that's all you have to do when you're solving for a specific or given time once you know where a mathematical expression. Okay? Let me know if you have any questions.